Hey there, welcome back. Sadly, or thankfully, depends on how you look at it, we're getting very close to the end. The only thing that we have left is implementing the WI function, which is the last filter. So I briefly explained what the WI filter or subfilter does, and I'll explain it just one more time so that we are on the same page. So to make sure that we're on the same page. So let's look at the first guess here of the sample game. No, I try to make it larger, but then the keyboard takes over. So arrows. We've already taken care of the O and the E, so we know that at this point, when we are applying the WI subfilter, we know that the O and the E have been taken care of, and we only have words that contain O's and E's in the correct positions. And we also know that we've already thrown away words that contain an S in this position, because an S cannot be here. So the only thing that we have left is making sure that the words do have an S somewhere, and that they do not have A's, nor R's for that matter. So WI is going to check if we have the wrong intersection or not. Or it's going to filter out the words with the wrong intersection. So this is what we need to do. Now APL very conveniently has a intersection function. So if I have something like 1, 2, 3 here and then 1, 2, 4, 5 here, we already have an intersection function. However, much like membership, the intersection function doesn't care about the quantities of the elements. So when we are computing this intersection, the thing that is done is more or less this. Is there a 1 on the right? Yes, there is, so let's have it there. Is there a 2 on the right? Yes, there is, let's have it there. Is there a 1 on the right? Yes, there is, even though we already compared it to this one. So we put it there, and the same thing for the next one. So this intersection is not enough, because we need to make sure that the intersections between the candidate word and the letters that we are taking a look at, and maybe I'll just do this and this. So we're taking a look at OSE. Sorry, not OSE. We're taking a look at ARS. We need to make sure that the S is there and the A and the R aren't. However, if we have something like, let's see, I have a guess and the score here. Right, if we have a guess like this, A, B, C, B, A, and the score like this, then we are essentially ignoring the B, because it's already taken care of. But then we are left with an A, a C, a B, and an A. So notice how there's 2 A's in there. It's the first one and the last one. And so when we check for the intersection, we need to make sure that the intersection yields one and only one A, because we need one A, but we don't want the second one. So we need to implement some sort of progressive intersection to make this work. And after we do make use of a progressive intersection to make sure that the intersection works, we need to compare the intersection with what we really wanted. And what we really wanted was just the letters that are scored with a 1. So in essence, the thing that we take into account is we take the guess and we only use, or we use all of the letters that were not scored with a 2. So we are going to use these letters, and after we do the intersection with the candidate word, we need to check it against what? Against the letters that were scored with a 1, because those are the ones that should show up in the intersection. So we're going to take this, intersect it with all of the candidate words, and make sure that those intersections only yield this single A. So this is what we want to do. Now, this is not very difficult, difficulty is relative. I've already given away a hint regarding the progressive intersection. So what I'll do is I'll let you think about it for a bit, and then I'll show you how I've done it. All right? So good luck with that, and talk to you soon.